Welcome all the students. Today we are going to learn the session or the topic that the part of the unit number 3 is two-dimensional geometry transformation. We are going to learn the 2D transformation, okay, the things which comes under the 2D transformation. We are going to consider the basic transformation, two-dimensional basic transformation. Under that, we are having the point translation, we are having the point rotation, scaling. So for all this translation, rotation and scaling, we are going to learn the matrix representation and the homogeneous coordinate system for all these things. Okay, then we are having the point composite transformation, and then we are going to learn the point reflection and sharing. So these are the 5 transformation that we are going to learn. So today's session we are going to start with our first basic transformation that we call it as 2D translation. Okay, so we are going to start with the topic 2D translation. Okay, so I'm moving to the first slide. Before we start with the 2D transformation or the translation part or basic, let us understand what is the 2D transformation. Okay, so we are considered the point is what is transformation. Okay, now the computer graphics provides the ability, okay, to transform. So the with the help of the computer graphics packages or computer graphics method, okay, we need to transform the points, lines and objects. Okay, so there is need for us to transform the point, or rather we can say transform the object. Okay, what is general meaning of transformation? Okay, transformation means to change. Okay, in simple word we can say transform means to change. That is, it simulate the movement. Okay, so we are going to simulate the movement and we are going to manipulate the object in the plane. Okay, if 2D plane, then it is XY plane. If it is 3-dimensional transformation, then it is XY and Z plane. Okay, so we need to, or what we are going to do is we are going to simulate the movement and we are going to manipulate the object in the plane. Okay, and that is called as the transformation. Okay, now whenever I want to transform a point, okay, so we first understand what is the how the point is represented, okay, in the coordinate system. Okay, so the first point that we are going to discuss now is representation of a point. In two-dimensional coordinate system, any point is represented in terms of x and y. So I represent any point in the two-dimensional with respect to or in terms of the having its x value and y value. So in terms of x and y coordinates. Okay, how we represent the point? We generally called as the point in bracket we write x comma y. The point is x comma y can be converted. Okay, now if I want to transform the point or if I want to transform the object, I need to represent it in the form of the matrix. Okay, so the point x comma y can be converted into matrix in the following 2 ways. Okay, so how I represent it into the any point is represented in the matrix form is, so I'm having the first option, it may be the row measure matrix. Okay, so matrix with a single row, we are having a matrix single row. How we represent it? So in the matrix form in a single row I write here x comma y, x and y. So in the matrix I'm having the point x and y. Okay, so this is nothing but it is having 1 by 2. Okay, so it is having, we can say it is a row measure matrix. I'm having a single, we can say rather it as a column. Okay, so column, or we can say it as a in the form of the row. I'm having one row, okay, which is having represented by xy. So I call it as the row measure matrix. Okay, now at the same time I also represent the point in the form of column measure matrix. Okay, it is possible to represent it in the form of column measure matrix, that is the matrix with a single column. So instead of using the row, I will use the column here. Okay, and in that column I'm having this value x and y, so it is going to be 2 by 1 matrix. If I represent with the row measure matrix, it will be 1 by 2 matrix. If I represent in the form of the column measure matrix, then it will be a 2 by 1 matrix. Okay, so in this way, because if I want to transform my point, okay, what is necessary? I must represent it in the form of the matrix. Then I will find out what is my transformation matrix. If it is I am applying translation, I apply the rotation, scaling, the appropriate transformation matrix. I multiply my point with that transformation matrix and I will get the transform point or transform object. Okay, so we represent the point in the form of the matrix. Okay, for the purpose of the transformation. Okay, so these above two matrices are frequently called as the position vector. We are calling this as the position vector, which is represented by a row measure matrix or it is represented by the column measure matrix. I can use this as well as this to represent my point. Okay, so let us move to the next slide. So I'm just moving to the next slide now. So we have seen how we are going to represent the point. Okay, but now we are going to look at how representation of any 2D object. Okay, not only the point, we have to represent the object. I may have an object as a triangle, I may have a rectangle, I may have a square, I may have any type of the polygon. So I want to represent the 2D object so that I can apply the transformation on that object. Okay, suppose we want to represent any rectangle in a matrix form. So if it is rectangle means I'm having the 4 points. I have to represent all the 4 points. Suppose we want to represent any rectangle in the matrix form, then the 4 vertices, or this now what I have told is 4 points or 4 vertices of the rectangle will be represented as. I may use the x1, y1 to represent first point or A point, x2, y2 to represent the B point, x3, y3 to represent the C point, and x4, y4 to represent the D point. So I'm just going to represent the 4 vertices of the rectangle A, B, C, and D. Okay, and it is how it is represented in matrix form. It is shown below. Okay, so just look at this. So this is what we are considering here. So this is what. Okay, so I'm having the figure that is 4 vertices of a rectangle whose only 2 opposite vertices are known. Okay, so suppose I consider this is my A point having the value x1, y1. So how it is represented into the matrix form? So it is represented in the matrix form. Okay, now as here we have written, we may use the row measure form or we can use the column measure. But here we are represented it in the row measure form. Okay, so we have represented as row measure form of the matrix. Okay, so this is my complete object is represented here. So this is my A point, this is the point B, C, and D. Getting me? So A is having the value x1, y1. So this is my A point having the value x1, y1 is represented. This is my B point which is having the value x2. Okay, so it is considered as x2 and y1 because the y value is not going to change. Okay, only x is moved from x1 to x2, y value remains as it is. So I'm having x2 comma y1. My C point. Okay, so this is my point C. Okay, so I consider this is my C point which is having the value x2 and y2. x2 is changed, y is also changing from y1 to y2. So C point is having the value x2 and y2. And this is the D point which is having the value x1 comma y2. x1 is same, x value is same here, but the y value changed from y1 to y2. Okay, so this is what, or this is the way, okay, we are going to represent the object in the matrix form. It may be the row measure form or it may be the column measure form, but here we are considering it as a in the form of the row measure matrix. Okay, so in this way it is represented. If I'm having a triangle, okay, suppose I just show that I'm having a triangle. Okay, so suppose my object is a triangle which is having the points A. So this is my point B and this is my point C. Getting me? So in the same way, in my representation object, I will have only now these 3 values in my matrix A, B, and C. Getting me? Now suppose, so what I am going to do, how I am going to represent this is I just going to show it here. Okay, so this is my first point is A. Getting me? Now suppose A is having the value, suppose I have taken the value of the A is 100 and 100. So X value and Y value of the point A. Okay, if I consider it as 100 and 100, I just take both the values are 100 and 100. Okay, it is represented. Okay, now suppose I want to find out the B point. Okay, in this particular case, what is the B value? the value, suppose I consider this is in x direction and this is y direction, x value will be obviously changing, y value is not changing. So suppose I consider this value is 100, this x value is 200. So I represent the point here it as, okay, this is 200. Okay, y value is not going to change, so this will remain 100 as it is. Okay, so this is also 100. This is also having the same value. Now if I consider C point, you can find that the C point is having the value, so it is represented in the matrix form as this is C. Okay, it is having the x value in between A and B. So A value is moving, x value is moving from A to B with 100 to 100. So it is in between, so I may have this value as 150. Getting me? So my C value is having the x value. C point is having the x value as 150 in between 100 to 200 and about this value. Okay. Now here, if I'm going to consider this is my 0, 0. Okay. So if I consider this is my 0 and 0, this is my x direction and I'm moving into the y direction. Okay. So suppose this y value, this A point is having the value 100, x value is 100, y value is 100. Okay, B value is having the x value 200. So obviously for the C point, x value is 150 and this is my y value. Okay, so this is y value 100, so I may take this y value as a 200 or I may take it as a 150. Okay, so suppose I take it as a 200, okay, then my y value of the point C is 200 and this is the way my 2D object is represented. Okay, so depending upon the number of vertices it is having. Okay, so if it is having a triangle, it may have 3 vertices. If it is a rectangle or the square, it is having the 4 vertices. It may be any polygon. So accordingly, we are going to represent it in the form of the matrix. Okay, so this is the way we are representing the 2D object for the purpose of the transformation. Okay, so now we are moving to the next slide to understand 2D translation, how I can perform the translation, because there are the 3 basic transformation. One is translation, then rotation, okay, and scaling. Okay, so we learned this as the 3 basic transformation and then we are going to learn the reflection and shading. Okay, so let us move to the next slide to understand 2D translation. So what the 2D translation? A 2D translation is applied to an object by repositioning it with respect to x and y direction. So translation means I want to move, I want to reposition the object. Translation means I want to reposition, I want to move the object with respect to x and y direction. Okay, now we translate the 2D point by adding the translation factors. So what I'm going to use is I'm going to use the translation factors. I'm giving the name of the translation factors as tx and ty. Okay, so this tx indicate translation in x direction, translation factor in x direction, and ty indicate translation factor in y direction to the original coordinate position x and y to move to a new point. So after translation I will get the value as x dash and y dash. Okay, so this is what we are going to consider. Okay, now if you are considered, just look at this particular diagram. Okay, before I moving to this formula, look at this diagram is translating a point from position P to position P dash with the translation vector T. Okay, what is my purpose? This is my x direction value, this is my y direction. So this is the point I want to translate. I want to translate this point P. Okay, I want to move this point P to the P dash. Okay, I want to move this point from this position to this position, reposition the point, or I want to move the point to this. Okay, I will do this by applying the transformation or translation vector T. So this T is having the 2 values. What is the value of this T? It is having the Tx. So I want to translate in the x direction how many values, and Ty. Okay, so what is my, suppose this P is having the value. Okay, what is the value of P? It is point is P is having the value x and y. Getting me? X and y, these are the values of original point P, and P dash is now having the value that what we are going to consider is x dash and y dash. Okay, so this p dash is having the value x dash and y dash. How I will get x dash? So this is the formula we are having. X dash is equal to x dash is equal to x plus tx. So we are going to apply the translation factor to x by adding. So this addition is important. So in translation, 2D translation, what we are going to do is we are going to add the translation factors tx and ty. So x dash is equal to x plus tx and y dash is equal to y plus ty. Okay, y dash is equal to y plus ty, x dash is equal to x plus tx. So I am adding the tx and ty into the x and y respectively. Okay, so we can express a translation equation as a single matrix equation by using the column vectors to represent coordinate position and the translation vector. So now I have just explained it, okay, as an equation, but in the matrix form how we are going to represent it. Okay, so that's why we are just going to learn this. Okay, so just look at this in the matrix form how it is represented. What is my p? P is my original point. It is represented by x1 x2, or we can say it is represented by x and y directly. Okay, so I may consider it here it is represented as x1 x2, or maybe it is represented as x and y. And what is my p dash? My p dash is my point after repositioning, point after translation. That will be x1 dash and x2 dash, or maybe you can say it as x dash and y dash. Okay, so which translation factor we are applying? We are going to apply the translation factor tx and ty. So this is my transformation matrix or translation matrix is having tx and ty. Okay, this allows us to write the two-dimensional translation equation in the matrix form. What is the p dash? So I can write the p dash is my transform, means after transformation, transform point p dash is equal to p. Okay, what is my p? That we are having the p value is nothing but x1 and x2, plus I'm going to add the tx and ty into it plus t. Okay, so I will get this particular form as p dash is equal to p plus t, which is I represent here. Okay, so it is very simple. What we have to do in a two-dimensional translation is we just have to add the translation factor tx and ty into the x and y direction. Okay, suppose I consider this p dash is having the x value. Okay, so this difference, suppose I want to move the point in the x direction by 100. Okay, so my what is my tx value? So my tx value, getting me, my tx value is equal to 100. Okay, suppose this is my displacement in the y direction, this is y, this is y direction. Okay, and suppose the displacement is 50. Okay, I want to move the point p into the y direction 50, then my value ty, translation factor ty, is nothing but it is equal to 50. So my tx is 100, ty is 50, so I want to move this point into the x direction by 100 and y direction by 50. So these are my translation factors. So these are known as, here we have written it as translation factor. So we have to take this translation factor so that I can move the point or I can move the object. Okay, or move means I want to translate the point or object into its appropriate position by considering the translation factors. Okay, so I hope all of you understood it, how we are applying the 2D translation. Okay, so let us move to the next point or next slide to continue our discussion of 2D translation. So now I'm going to consider the example here. Okay, so I think just now we have shown it. Okay, but now we have just want to show in the form of the object. Okay, so how the object is translated. Okay, so a 2D translation example. Okay, I want everyone to just look at this particular diagram. Okay, now here why we have considered this example, because my translation factors tx and ty may have the negative value also. It is not necessarily I want to translate into the positive values, or I may move to the negative values. Okay, so consider this is my object. Okay, so this is my diagram A, this is my original object. So A represents the original object. You may consider this is having the value A, B and C. If we consider that this is the value A, triangle is having the value A, having the value B and having the value C. So this is my triangle ABC. Okay, now this triangle I want to move, I want to reposition into x and y direction by having the factor tx and ty. Okay, now here it is written, moving a polygon from the position A to position B. I want to move the polygon from position A to position B with the translation vectors, with translation factor minus 5.50. Okay, I'm just taking it minus 5.50. So what is my tx value? My tx value will be minus 5.50 and my ty value will be plus 3.75. So it is not necessarily the tx and ty should be integer, it may be any floating value I want to move. Okay, so you can find that suppose my x value, whatever the x value, I'm just having the minus 5.50, so it is coming. Suppose I consider here it is having the value somewhere as the 7 or 8 here. A point is having value somewhere here. I go for minus and now I will get the x value over here. Similarly, it is apply everywhere. Okay, what about y? For y, I'm going to add 3.75. Okay, so this is my y value. Okay, suppose this is y value is 2. Okay, in the y value if I want 3, means it is 3, 4, 5, 5 point something or 5.75. You can find it here. It is having the value 5.75 over here. That is my y value. Okay, so this particular example shows that I can translate the object, I can move the object, okay, any triangle or the object with respect to tx and ty. Okay, and this tx and ty not necessarily positive values, it may be a negative value, it may be positive value, or it may be floating point value, not necessarily integer value. Okay, so what is my tx here in this diagram? It is minus, I have taken this value as minus 5.50. Okay, minus 5.50 is the translation factor now. Getting me? And what is ty? Ty is positive value. I want to move into the positive direction. It is having the value 3.75. Okay, so it is not necessarily integer value. I can take the floating value as a translation factor also. Okay, and I'm going to move this triangle. Okay, now you have observed that in the translation, oh, that is what we are here. Translation is this rigid body transformation. Means I'm not going to make any changes in the size of the object, not in the shape of the object. Everything remains as is. Only I'm going to move the object. So translation is called as a rigid body transformation that moves the object, that reposition the object, moves the object without deformation. So I'm not going to change the shape of the object. I'm not going to change the size of the object. So it is called as without any deformation. Okay, I'm not going to deform the object. Okay, I'm just going to move the object. Okay, so it is called as translation is a rigid body transformation. Okay, that is what we are going to do here is we have done the every point on the object, every point on the object. Okay, suppose I'm considering it as a vertices a, b and c. I think it is considered as a every point. Okay, all the points on this particular triangle, everything on this triangle, each point is now translated. So that is every point on the object is translated by the same amount in the x and y direction. So A is translated in the x direction by minus 5.50. So B is also translated in x direction by same point value, minus 5.50. C is also translated with the same value. So every point is on the object is translated by the same amount. Okay. Suppose in the y direction we have added 3.75, means every point is added y value 3.75 and we come to the new value or new point. Okay, so this is what we have considered the example of 2D translation. Move the object in x and y direction, okay, with the factors translation factor tx and ty. The translation factors may be negative, okay, not necessarily positive, as well as this translation factor may be a floating point value. Okay, so that is what we have considered in this particular 2D translation example. Okay, so I just continue the discussion of the two translation. So we are moving to the next slide to continue our discussion of the 2D translation. Okay, now whatever the thing that we have learned, okay, for the 2D translation, Now we understand what is mean by the homogeneous coordinate system. Okay, because this is going, we are going to learn for all the translation, the rotation, scaling everywhere, and that is what is mentioned. Okay, in the syllabus or in the point is we have to consider the homogeneous coordinate system also. Okay, matrix representation and this. Okay, so let us understand 2D translation and homogeneous coordinate. Okay, why homogeneous coordinate system is required. Okay, the origin of the coordinate system does not change with respect to all transformation. My origin, that is 0 0 of my coordinate system, will not change with respect to all type of the transformation. But when origin is changed, suppose I want to perform the transformation where I want to change the origin. So I want to change the origin other than 0 0. I want my origin of the coordinate system should not be 0 0, but it is other than 0 0. It is necessary to be able to modify the position of the origin. So what is necessary, that it is able to modify the position of the origin, that is to transform every point in the 2D plane. Okay, and now, okay, and now what we are going to do is how we can achieve. Suppose I want to perform all the transformation, okay, where my origin is not 0 0, means I want to perform transformation other than the origin 0 0. Okay, then how I am going to achieve this? So what we are going to do is, this can be achieved using, so I'm considering x dash is previously what we are considered, x dash is equal to ax plus cy only, but now I am adding this m plus m to reposition it from not 0 0. My origin is not 0 0 now, but origin is having the x value m, okay, and y value n. So I'm having this formula, y dash is equal to bx plus dy plus n. X dash will be changed as ax plus cy. Okay, so a and c constant will be added into x and y plus m, and y dash is equal to bx plus dy plus n. Okay, definitely we are going to see the matrix representation of this. Okay, on the next slide we will see how it is represented in the matrix form. Okay, now it is not possible. Suppose this is the case. Suppose I want to apply x dash and y dash should be added with m and n, so that I can change my origin from 0 0 to m and n values. By m and n values, I want to change my origin. Okay, it is not possible to introduce the constant m and n into 2 by 2 transformation matrix. So whatever the 2 by 2 transformation matrix I am using, okay, transformation matrix, whatever the 2 by 2 transformation matrix I'm using is now not suitable. I'm saying it is not suitable if I want to introduce the constant m and n, then it is not suitable. Therefore what we have to use it, therefore we introduce the homogeneous coordinate system. To accommodate this m and n value, we are going to introduce, or we are going to use the homogeneous coordinate system. Okay, so that is the reason, okay, that we are having, or we are going to use homogeneous coordinate system. Okay, now what is this homogeneous coordinate system? The homogeneous coordinates of a non-homogeneous coordinate. Suppose now in non-homogeneous coordinate, how point is represented, I represent it as x comma y, x and y. So my point p is xy, now are represented in homogeneous coordinate system as x dash, y dash and h. So this H stands for the homogeneous coordinate system. So we are added one more value here as H, so that to convert it into not 2 by 2, but we should use 3 by 3 transformation matrix. Okay, to convert the point from 2 by 2 to 3 by 3, we are having the X and Y, which is non-homogeneous coordinate system, is now represented in homogeneous coordinate system as X dash, Y dash, H, where what is X value? X is equal to x dash divided by h, and y is equal to y dash divided by h. Okay, so if I take this h value is equal to 1, then obviously x is equal to x dash and y is equal to y dash, means it is having the same value. So generally we are going to take this h value as 1. Okay, what is general way we are going to represent it in the form where this homogeneous coordinate h value is considered as 1. That is what we are having. The set of homogeneous coordinates are always represented in the form x, y and 1. Okay, what is in non-homogeneous coordinate system? In non-homogeneous coordinate system, I represent a point as x and y. Okay, it is having only two values x and y, but in homogeneous coordinate system now I am having the values x, y and 1. So this 1 indicate it is a value of h. Okay, it is the value of h and it is represented as value 1, general represented as value 1. So my point is now represented in homogeneous coordinate system as x, y and 1. This one is represented, or 1 indicate h value. Okay, now this value may be other than 1, it may be 2, maybe 3, maybe 4. Okay, then how it is represented? I want everybody to just concentrate on the example. What this example shows, suppose I am having the value 4 to 1. Okay, so my x value is 4, my y value is 2 and my h value is 1. Okay, so what is my, this is my x dash. So what is my x value? X is equal to x dash by h. Okay, so my x dash will be 4 divided by 1 means 4. So what is my point represented? My point represented is 4. 2 divided by 1 means it is 2. So I am going to represent the point 4 comma 2 in the homogeneous coordinate system as 4 to 1. The same point can be represented as 8, 4 and 2. See, 8 divided by 2 means I will get this value as 4. 4 divided by 2 means I will get this value as 2. So this 8, 4, 2 also represent the same point. Similarly, 12, 6, 3 also represent the same point, because 12 divided by 3 I will get the 4 and 6 divided by 3 I will get the 2. Okay, so means this this one this one all represent the same point 4 comma 2, or also I can use h value is 4. So 16 divided by 4, 4 into 4 16, so I will get this value as 4, and 8 divided by 4 it is 2. So all these homogeneous coordinate system values 4 to 1, value 842, value 1263 and 1684. Okay, all these in homogeneous coordinate system represent the actual point 4 comma 2. Okay, but what is the general representation? Maximum time I'm going to use this value as 4 to 1. Okay, so this is 4 to is represented as 4, 2 and 1 in general homogeneous coordinate system. Okay, I hope we have understood what is homogeneous coordinate system. Okay, and now we are, our transformation matrix is converted from 2 by 2 to 3 by 3. Okay, so let us move to the next slide to understand what is my general transformation matrix 3 by 3 represented and how it is applicable to 2D translation, how it is applicable to 2D translation. Okay, so I am just moving to the next slide to understand the things in detail. So in homogeneous coordinate system, due to the homogeneous coordinate system, my general transformation matrix is now 3 by 3. Okay, so it is now not 2 by 2, but it is 3 by 3. How it is represented? So my transformation matrix, 3 by 3 transformation matrix is now having the value in one row A, B, 0, C, D, 0, M, N and 1. Diagonal value, this is 1. See, what was my previous 2 by 2 transformation matrix? This was my 2 by 2 transformation matrix. Okay, this was my 2 by 2 transformation matrix. This was my general 2 by 2 transformation matrix, but it is not possible to, it is not possible to represent, it is not possible to add the constant m and n. Okay, so that I can change the origin, so that I can change the original position. So we have converted our general transformation matrix from 2 by 2 to 3 by 3 transformation matrix. Okay, so this A, B, C, D will be my 2 by 2. Now that is converted to 3 by 3 by adding the 0 value here. This is 0, this is 0, diagonal value is 1, and now this is my M and N. Okay, that we have introduced. These constants are introduced. The same thing we have written here. A, B, C, D of upper 2 by 2 submatrix have exactly the same effect as discussed earlier as a 2 by 2 transformation matrix, and extra variable m and n are the translation factors in x and y direction. So I'm having this m and n is nothing but, now these are my translation factors, okay, which are represented in x and y direction. So this is what I have got the 2D translation in 3 by 3 transformation matrix. Okay, so let us understand this into the detail now. So now I can say that, okay, so with the help of this 3 by 3 transformation matrix, I can say the pure 2D translation matrix is allowed to shift the point at desired location. So now my transformation matrix for 2D translation, 2D translation transformation matrix will be, this is x, y and 1 is represented by my point. Okay, and this is my transformation matrix T. Okay, so this is my translation, two-dimensional translation matrix. Okay, is this diagonal values are 1 1 1, these are values are 0 0 0, and my value is m and n is represented. See, this m and n is nothing but, this m is nothing but, it is my tx. Getting me? This tx is represented by m, so I can write here tx, and this n is nothing but, it is my ty, translation factor x and translation factor y. So m is nothing but my tx and n is nothing but my ty. So these are my translation factor tx and ty. Okay, so what I'm going to add, I'm going to add x plus m, means I'm going to add x plus tx. I'm going to add y plus n, means y plus ty, and this value is 1. Okay, so this is what, so this indicates the 3 by 3 translation matrix, two-dimensional translation matrix. But instead of using 2 by 2, we are using it as a 3 by 3, considering the homogeneous coordinate system. Okay, by applying the homogeneous coordinate system, my value, my point is now not only x and y, but it has now changed to x, y and 1. This one represented as the value of homogeneous coordinate system, and my transformation matrix will be, diagonal values are 1 1 1, all the remaining values are 0 0 0, and this is my tx and ty. This is my m and n. M is the translation factor in x direction, n is the translation factor in y direction. Okay, so this is what my two-dimensional translation matrix. Okay, because if I add this m and n value, if I'm going to add the tx and ty value in the x and y respectively, obviously what is the effect? My object will be moved, my object will be repositioned from original position to transform object. So appropriate position in x direction, appropriate position in y direction, as per the values of m and n, that is tx and ty. Okay, so this is what the 2D translation matrix is represented. Okay, with the help of homogeneous coordinate system. Okay, and this is what I'm going to use as the translation matrix. Okay, T. So this is, I'm going to use this as a capital T. Capital T indicate the transformation matrix or translation matrix. Okay, and this is the way I can perform the two-dimensional translation. Okay, I hope all of you understood the 2D concept of 2D translation in detail. We have seen all the details of 2D translation example. Okay, then the basic translation matrix. Okay, then homogeneous coordinate system, how it is converted in the homogeneous coordinate system from 2 by 2 to 3 by 3 transformation matrix, and all the details. Okay, so next session, we are going to see how this 2D translation can be implemented using the C program, or rather we can see, going to see the C program implementation of 2D translation. Okay, thank you. I say thank you all.